right, class, today we're going to continue our discussion on vectors in the plane. The other day we talked about the norm of a vector, or the magnitude of a vector, and we talked about the component form of a vector. Today we're going to look at some vector operations, adding and those type things. We're going to look at adding vectors geometrically before we go to the algebraic portion. So we're looking at vector operations. We have two basic operations, vector operations, and they are scalar multiplication and vector addition, okay? We have others that we will talk about, but these are the basic operations. For example, suppose we have this vector v. Okay? Now, if I draw another vector half the size of v, then this is half of my vector v. Or if I draw a vector twice the size of v, then that's 2v. Okay? This is scalar multiplication geometrically. Okay? We cut down on what we cut down on. The way I draw negative v is if my initial point becomes my terminal point becomes my initial point, and I'm going in another direction. This is negative v. Okay? Geometrically, that is what that means, negative v. Have the same length, but I'm going where? The opposite direction. Okay? So basically, and this is just geometric right now. We're going to talk algebraically in a few minutes. Now, how do I add two vectors geometrically? Now, adding two vectors geometrically is not going to be so important, but we do want to show you how to do that. For example, if we have some vector u and some vector v, let's say going out like this, then the way we add u and v is that we copy our u vector, we connect or we move the tail or the initial point of this vector to the ending point or to the tail of this vector. So this thing will kind of move up, kind of like that. This is my vector v. We want to kind of draw it the way it's drawn. It has a little slant to it. And then if I go in here and I connect the initial point of vector u with the terminal point of vector v, then this yellow line represents for me the new vector u plus v. Now let's say that again. If I have two vectors u and v in space like this, and we're talking geometrically right now because we can add them algebraically, but we want to know where this geometric concept comes from. I still draw my vector u as it is. I move this vector v up here to where the initial point of vector v is sitting on the terminal point of vector u. Okay? And then I draw a line from the initial point of u to the terminal point of v, and that gives me u plus v. Okay?
If you were to make it a straight line?
The way these are, they would only be a straight line if those two vectors are parallel to each other. And then the drawing from the initial here to the terminal, that would just still be that straight line.
But it would make it longer if it were straighter, right? It would make the u plus v longer.
If it were straight, well, it depends on how u and v are both drawn up there. Because if they are parallel, then, and you put those heads and tails together, if that straight line is that line, and that's just the length of it. But here, they're not parallel, you know. They shouldn't be parallel. They look like they could be. Notice that this is somewhat of a straight line, but they're not exactly parallel, okay? But I don't focus so much on the geometric portion as I do the algebraic portion, but it's good for you to know where it comes from. So let's define algebraically this scalar multiplication and this vector addition. So let U be a vector in component form with components U1 and U2, and V be a vector in component form with components V1 and V2. And let K be a scalar. Scalar is the same thing as what? Constant, okay? Just a constant. Then U plus V in component form. I add U1 and V1. That gives me the first component. U2 plus V2 gives me the second component of that vector. So I add corresponding components. For scalar multiplication, some constant times the vector U, constant times this component form.
So the second one. And K be a scalar?
Yes.
What is K?
K is a scalar. Scalar is a constant.
I mean, as far as the graph.
It's just in what graph? Oh, here. This is scalar multiplication. Here, we look at V. The scalar here is 2. We double it. Here is 1/2. We half it. Here is -1. We go the opposite direction. So in physics, they call constants scalars. Okay, just another name for a constant. This, I can multiply my K by both of the components there. So this is the algebraic definition for scalar multiplication and vector addition. Now we have some properties. Just like we have properties of real numbers, like the associative property, the commutative property of addition and multiplication, we have the same thing for vectors. So let's look at some properties of vectors. So now, let U, V, and W be vectors. And let C and D be scalars. The first, this associates with the commutative property of addition for real numbers. U plus V equals V plus U. Does not matter the order we add them. W.
Okay.
We also have something relating to the associative property. I can get my sum of U and V and then add W. It's the same as adding V and W and then adding what? U. So it does not matter how I group the vectors, the addition is still the same. And the reason why these properties follow with vectors as well as real numbers is because what? The components of these vectors are real numbers. Number 3, U plus the 0 vector is just a vector U. Remember, 0 is the vector with component 0, 0. Yes?
Are these identities or you actually working problems?
No, these are properties.
Okay.
These are just properties. These are not problems, just properties. This is a 0 vector, the 0 vector.
So this was pretty easy.
And then we have an additive inverse. U minus negative U is what? The 0 vector. If we and the fifth property, if we get the vector du and then multiply by the scalar c, it's the same as multiplying these scalars together first and then multiplying it into their vector u.
What is the scalar one more time?
A constant, 2, 3, 4, just a constant. Any real number.
So it's whatever is back there. Like 4 and u, scalar would be 4.
Yes. Property 6, c plus d times u is cu plus d u.
How come on number 3 you got u and o?
The zero vector. The zero vector, remember we talked about yesterday, 0 is a vector that has components 0, 0.
Okay.
That's the definition of the zero vector. Because 0 is a scalar and it's a vector.
Okay, that's what confusing. I thought that was a letter. O.
No, 0. 0. I'm sorry. I said, 0. It's 0. The zero vector. 7. A constant times this sum of the vector u and v is cu plus cv. We can kind of like distribute the c to those vectors. And number 8, 1 times the vector u is just u, and 0, the number 0, times the vector u is the zero vector. Okay? The number 0 times a vector u, because when I multiply 0 times u1 and u2, I'm going to get what back? 0, 0, which is the zero vector. 0 is a vector as well as a scalar. And number 9, if I take the length of a constant times a vector v, it's the same as taking the absolute value of that constant times the length of that vector v. Okay? 1 line on either side is what? Absolute value. 2 lines represents length of a vector. Okay? So these are just properties. We also talked about a unit vector very briefly the other day. We said a vector is a unit vector if its length is 1. Well, how do we find unit vectors? How do we find unit vectors? So, unit vectors have magnitude or length 1. And to find a unit vector u in the direction of a non-zero vector v, then we divide v by the length of v. So what this is saying is that if I divide a vector by its length, it's going to make it a unit vector, okay? Okay? I can find a unit vector in the direction of v. Now notice I'm not saying I can make v a unit vector, okay? I can find a unit vector in the direction of v if I divide by its length, okay? Now, why would I want a unit vector? Well, once you get into certain problems in calculus, it's just going to be easier when that magnitude is 1. Okay, this is going to be a little easier. So you will get great use out of finding unit vectors. Now, we have some standard unit vectors. Now, right now, y'all, we're doing everything in the plane, x, y, okay? And I don't know in this course, I know once you get into calculus, they're going to extend the stuff to space, where you have what? X, Y, Z axes, okay? But we're just dealing with the X and Y axes, so we will only have 2 standard unit vectors, and they are defined to be I. That's the vector with components 1, 0. And J is component vector, standard unit vector 0, 1. Okay? So basically what that means is that in the plane, this vector going from the origin to here is I. And up here, if that's 1, the vector going from the origin to here is J. Those are my standard unit vectors. Okay? And we can write a vector in component form using I and J. Okay? This gives me a means of writing vectors in a different way than in component form. Okay? So as a note, any vector in component form can be written as a linear combination of the standard unit vectors I and J. Now, how many of us have to go and take linear algebra? You're going to see a whole lot of linear combination stuff in linear algebra. A whole lot of it. So what this is saying is that I can take any vector V in component form, okay? I can break this V down where I can bring out V1 and multiply it by that vector and bring out V2 and multiply by this vector. Now what I'm doing now is not a problem. It's just showing you that I can go from this component form to where I can write a linear combination. And what is a linear combination? It's where you can have the sum or difference of these vectors I and J. Okay? So, notice if I multiply V1, I have V1, 0, 0, V2, add them together, give V1, V2. So any vector in component form can be written in that way, where V1 times the vector I plus V2 times the vector J. I know it's a lot being thrown at you. We're going to some examples now. We haven't really done a single example today. All this has been just lecture. Now let's go back and let's do some examples. Okay? So, example, the first example today. Suppose we are given the vector U to have components 2, 3, and the vector V to have components 4, 0. And this is going to be a multi-step problem. Suppose I want to find U plus V. How do I find U plus V? I add the corresponding components, don't I? Right? I add, this is like my U1, U2, V1, V2. So my definition over there tells me I need to add U1 and V1, which gives me what? And then I add U2 and V2, and that gives me what? So that is the what? The sum of those two vectors. Yeah.
Can you put like 40 of those?
That's the answer. Okay? Part B. U minus V. which now we know that subtraction is addition. It's going to be U1 minus V1, which is what? U2 minus V2, which is positive. U2 minus V2, positive 3. Okay? 2 minus 4. U1 minus V1. How about if I have 2U minus 3V? Well, first of all, what is 2U? I multiply 2 by everything in U, I get what? 4, 6, right? What is 3V? 3 times 4 is 12. 3 times 0 is 0. And then when I subtract them, 4 minus 12 is what? 6 minus 0 is?
Wait, you subtracted 4 minus 12.
Mm-hmm.
Okay, and then 6 minus 0.
Mm-hmm. No, it's not. And it is a lot of information. It's a lot of information. Now, suppose, again, we're given, but now we're given that U is a vector based on our I's and our J's, and V is a vector based on our I's and our J's. So now they want us to find U plus V. And this equates to doing what? Kind of like combining like terms. I add my i's, negative 2i plus negative I is what? Negative 3i. And 1j plus 2j is what? 3j? Same thing.
Is that on the original part where it says example U equals?
Yeah, this is given. This portion is given.
I mean, is that just the J after the 2I?
Here?
Yeah.
Yeah, that's 2j.
I mean, you get the little.
And that's j. Yeah, this is j. 1j.
Are you putting vectors over the I and the J?
Yeah, because they are. And I didn't put one here, but yeah, they are vectors.
That's why I got confused on.
Oh, I'm sorry. They're vectors. They're vectors.
Yeah.
No.
You made the J out.
These are my arrows. Remember, arrows are, I need to. Same thing. It's where we can add vectors. Because see, this U, we can write this in component form as negative 2 what? 1. And this in component form as negative 1, 2. Remember? We can write any vector as a linear combination with I and J. So we can write that in component form. And so basically that's what we're doing. We're combining the I's and the what? The J's. So some of these problems they're going to give you in component form, and some they're going to give you as linear combinations. And however they give it, that's the way you need to write your answer. And notice what? Negative 2 minus 1 is negative 3, and 1 plus 2 is 3. But because they gave us these vectors with linear combinations of I and J, then we need to give our answer like that. It's just two different notations. Just two different notations. And what's U minus V here? I subtract now 2 minus a negative 1, which is what? Negative 1i. And 1 minus 2 is what? Negative j. And they're going to do that. They're going to give you some things in component form with the little arrows, and then they're going to give you some like this. But essentially, you're doing the same thing, okay? They mean the same thing. Next example. Let's find a unit vector in the direction of this vector v, which is 5, negative 12. So by my definition over there, a unit vector u is the vector v divided by what? The length of v, right? So I need to find the length of v. What's the length of v? We use the distance formula, but here, since this is in component form, it's the square root of 5 squared plus negative 12 squared, right? Negative 12 squared is 144, 5 squared is 25, 144 and 25 is 69, 169, square root of 169 is what? 13, which means now I have 5 over 13 and negative 12 over 13. And this is my unit vector in the direction of v. Okay? Yes. Because really we're we have this 13 at the bottom, and that becomes our denominator.
Where's the 5 and negative 12 in numerator?
It's v. It's the vector v. We then divide these components by the length to make a unit. How are we not supposed to use this formula? Because we just said that to find a unit vector u in the direction of a non-zero vector v, then we divide v by its length.
Alright, so how are you going to do 5 squared plus 12 squared?
Oh, because the other day, remember, the length of v, if this vector is in component form, it's the square root of v1 squared. That was a formula we were given the other day. You're going to be given several formulas with this vector stuff. That was a formula from the other day.
They'll be divided, right?
Oh, I see. Well, is this
We'll talk about it later.
b2 over 1 plus b2 over 2?
Huh?
Oh, okay.
Okay, any other questions before we move on? Okay. Let's look at another one. Let's find a vector v with magnitude being 6 and the same direction as u, which is given to be negative 3, 3. Okay? Now what is this telling me? Find a vector v with magnitude of 6 and in the same direction as u, which means, first of all, if I go ahead and make u, or find a vector in the direction of u that's unit, then I'm almost there, am I not?
On that v, vector v, what's the little double lines on each side?
Magnitude or length.
Okay, that's just another way of saying magnitude. Okay. All right.
So, first of all, I need to find a unit vector. And once I find a unit, then I can make the direction or the length 6 by multiplying the components. So let me find, so the first thing I want to do is find a unit vector in the direction of u. Okay? So, which means I need to have u divided by what? The length of u. So what is the length of u? Square root of what? 18, because we square this, we add. So the square root of 18 can be reduced. The square root of 9 is what? 3, and we're left with the square root of 2. Which means now I can have negative 3 over 3 square root of 2, positive 3 over 3 square root of 2. And we don't want to leave it like this. We want to simplify. I have negative 1 over square root of 2 and positive 1 over square root of 2. And I can rationalize here, can I not? Multiply both numerator and denominator by what? Square root of 2. So this becomes negative square root of 2 over 2 and positive square root of 2 over 2. Okay? So I have found a unit vector in the direction of u. Now, it says that I want my new vector, or I want to have a vector v that has what? Length 6. Which means I need to multiply this vector because it's unit now, which means the length is 1. And if I multiply by 6, then my length is now going to be what? 6. So let me multiply this vector by 6. So if I multiply this by 6, I'll have what? Negative 3 square root of 2 because 2 will go there 3 times. And I have positive 3 square root of 2. So that is a unit vector. No, it's not. It's a vector in the direction of u with magnitude what? 6.
Okay. I'm going to back up about 100 feet. How do you get the square root, Adrian?
Okay. Here we did what? We did negative 3 squared, which is what? 9. 3 squared, which is what? 9. And 9 plus 9 is?
Oh, okay. You don't
18.
multiply me?
No, you add. You add. See here? V1 squared plus V2 squared takes square root. We just skipped a step.
That's what I was thinking, but then, I mean, I got the 9, squared part, right?
Mm-hmm.
But I was thinking wrong, I was like, thinking that you multiply and get it. So I was coming up to 81 instead.
Oh, no. Add. Because what you need to do is think about the distance formula. And in distance formula, we do add. Because it's based on the distance formula. After we get the...
You have to go, that formula is not given the vector u over the distance.
Is it? No, it's not given in the problem.
It's in your
Mm-hmm.
list of formulas.
Mm-hmm. Question in the back.
Yes, how did you, I know, like you multiply the 6 to get the vector v.
Mm-hmm.
Multiply the 6 and like how did you do that?
How do we... Okay, you understand this.
Yes.
We just multiply both terms by 6.
I know, but I get like the negative 4 when you're calculating.
No, we want exact answers. 2 goes into 6 3 times. Reduce those fractions.
Oh.
Okay.
Mm-hmm. Yep.
So all a unit vector is take a vector and shrink it down to length of 1.
Uh-huh.
Is that correct? It's making it back.
Uh-huh. Yes.
And why is it important to find a unit vector in that problem?
Well, they wanted a vector with magnitude 6 in the same direction as u. Remember, when we make, we're not making u a unit vector. We are finding a unit vector in the direction of u. So that gives me, this portion here gives me a vector that is unit in the direction of u. And they want it in the same direction as what? U. So this does this part. Okay? In the same direction. Then they want the magnitude to be 6. It's now 1. And I must have everything by 6. But they want it, that it's very important because in the same, we're not making u unit. We're finding a different vector that is unit, but in the same direction as u. Okay? Uh-huh.
You just took that 2 and divided into 6 to get that.
Yes.
Okay.
Mm-hmm.
So I think.
We okay now? All right, let's look at another one. Let's find the component form of this vector V, which is negative U plus W, if we're given that U is what? 2I minus J, and that W is I plus 2J. So what is this problem asking us to do? First of all, they're asking us to find what? Negative U, right? We need negative U. What's negative U? Well, we multiply U by negative 1, so I get negative 2I plus J, right? And they want me to add this to my W, that's given. And when I add, I do what? It's kind of like combining like terms. Negative 2I plus 1I is what? Negative I. 1J plus 2J is 3J. But they wanted what here? Component form. And the component form, we just take our what? We take our coefficients. Negative 1 and positive 3. Okay? This is the answer, but they say, hey, go a step further because I want it in component form. Was that confusing?
No, why do we get rid of the I and the J?
Because they want it in component form. That's why. If they had just said, find V, you know, if U is this and W is that, we could have left it at that previous step. But because they said put it in component form, with these arrows, this is component form here.
So those arrows symbolize take out your vectors or whatever?
This is a linear combination. No, component form of a vector means that your initial point is at the origin.
If we taken the standard, what do you call those, the standard vectors, I, J, made so it's negative 1 times I plus 3 times J, and added them up like that, the other property, then that would be the answer we got.
You had changed those to components first, like you said, and then add them. It would have been the same thing.
I was busy trying to write all this down, I'm kind of lost.
Yeah, I'm already
So we
right
could
now.
kind of say you skipped a step, sort of. If we actually changed the I and the J to component form before we added them together.
Yeah, you can do that. You can change it to component form. But I would think it would be easiest to go ahead and get the negative U and add it to the W and get this form, and then change it to component.
I just can't get my brain around it right now, so.
But either one, it's okay to do it either way. It's okay to do it either way.
I understand where you got the negative I plus 3J.
Okay.
Now how to get the next step?
Okay. If you remember, we had on the board that if we had V in component form, V1, V2, it's the same as saying V1I plus V2J. It was some work in between, but essentially this is where it came from, and that was somewhere on the board over there, and I just erased it, but we've erased it. And this is saying that I can write any vector in component form as a linear combination. Well, it's written as a linear combination. They say, well, give me component form. So we take the V1 portion, the V2 portion, and we put it in our arrows.
Is that why you chose to use I's and J's instead of U's and W's?
We use I's and J's because it was given in the problem, basically. We're using W's. What are you talking about?
Or vector V?
Yes, U is defined to be 2I minus J. And W is defined to be I plus 2J.
Plug it in,
Mm-hmm.
and you solve,
Oh,
put
wait.
it in linear form.
So you're multiplying.
We're adding. Well, we're multiplying by negative 1 here.
And then it's telling you what U and V are, so they're
Mhm.
plugging it in, and you just solve the equation.
But you need negative U, so you do have to get the negative, which is negative 2I plus J. And then you
just
add
move
to
the
it.
negative over to be negative 2 I, since it's the same thing. I 1 0 J 0 1.
What are you saying? Wait one second. What are you saying?
right there where it says, vector U,
Mhm.
says the same thing as vector V.
No.
No?
No, it's not the same thing. Here, we want to find V. V is negative U plus W. So here, this is my negative U portion here, and this is my W portion. They gave me U, and I had to do what? Get the negative of U, which means getting the negative of this, which is negative 2I, the negative of this, positive J, and they gave me W. And then they say add those two together. And we just add. Negative 2 plus 1 is negative 1I. 1J plus 2J is 3J. And this here is a correct answer. But they said that they wanted to see this answer not as a linear combination, but in what? Component form,
I understood that.
which is this.
I just got confused on the first part when we started linking all this up together.
That'll always work out if it's fully coefficient seven.
Yes. Mhm. Yes. All right. Are we ready to talk about something else? Well, we got to. We need to finish this up today. No, we have another topic. Direction angles. I told y'all.
I think I could stop.
I told y'all this was a pretty long one. It's a pretty long one.
We separated this more examples, that's
No, because we're on schedule and we have to do the next portion next time. We're on schedule. We got to get it through. Direction angles. If U is a unit vector such that theta is the angle counterclockwise from the positive x-axis to U, this vector U,
What's that ST mean?
such that the terminal point of U lies on the unit circles and U is equivalent to the point XY, and we're going to draw a picture, and the picture would clear it up for us. If we have the coordinate axes here, and if I have some vector U, and they tell me U is a unit vector, then this is my terminal point of U, but this also represents for me some point XY. Okay? Now, if I drop a vertical line here, I form a right angle. This distance here is X, but X from our unit circle is what? Cosine theta. This distance here is Y, but Y from our unit circle is what? Sine theta. So now this XY can also be considered cosine theta, sine theta. This is kind of like Y on the unit circle. The first coordinate is sine, the second coordinate, first coordinate is cosine, second coordinate is sine. Which I can also write this as a linear combination with I and what? J. So this theta is called the direction angle of the vector U.
So, that little graph you drew, that's the answer to that problem?
This is not a problem.
Oh.
This is just lecture material. Whenever I say example, that's a problem. This is not a problem. This is just telling us some more information so we can do some more problems. Okay? This is not a problem. This is just, we're formulating these definitions that we're using to do the problems. We're going to use this stuff in a minute. All right. Maybe we can go on a little further because we have a few more things to talk about before we do some more problems. Okay? Suppose that this unit vector u, that u is still a unit vector, and if v is any vector that makes an angle theta with a positive x-axis, it has the same direction as u, and we can say this vector v is going to be the length of v times cosine theta sine theta, which can also be written as the norm of v cosine I plus the norm of v sine theta j. Okay, both of those mean the same thing. Now, from this, they want us to find sometimes this direction angle, okay? And I know cosine and I know sine, so remember that tangent is going to be what for us? Tangent is what? Sine theta over cosine theta. So we need to remember that in finding this theta. So sine theta, cosine theta is the outest portion here. Well, let me state this in a different manner because it will get confusing with the way. We can go a step further here and just call all of this A and call all of this B. Okay? So now we can say that tangent theta is B over A. So it's not just this cosine portion, it's going to be this cosine times that magnitude portion, okay? And that's how we're going to determine somewhat with this tangent theta. Because what they want us to do ultimately is they're going to give us a vector V, and they say find the magnitude and the direction angle. And the direction angle may be given, and the direction angle may not be given. And let's look at a couple of examples. Huh? The last few. Yeah, it's not just one. Here you want to find the magnitude and the direction angle of V. The first example is going to be very easy. They give us vector V being 8 times cosine 135 degrees I plus plus sine 135 degrees J. Okay? Now, with this example, everything is clearly stated for us here. Because here the magnitude of V will be 8. And our theta is explicitly given to be what? 135 degrees. Notice, explicitly given for us. The magnitude of V, notice here they have 8 outside in parentheses, but if we distribute this 8 through, we'll have 8 cosine 135, 8 sine 35. This 8 is what? The norm of V. Theta is the angle. So that was pretty simple, okay? Explicitly given. But the next one is not so explicitly given. This is the answer here. But the next one, when we have a vector like that, negative 5i plus 4j, none of that stuff is explicitly given. They still want us to find what? The magnitude, and they still want us to find what? Theta. Okay? We can find the magnitude easily of this vector. It's what? Negative 5 squared plus 4 squared. We take the square root. So we have what? 25 plus 16 is what? 41. So that's the first portion of the problem, is to find the magnitude. Not so difficult. Now we got to think about finding this, what? Tangent theta. We need to find theta. Now notice we said tangent theta was what? B over A, right? Where here, B, A represents everything in front of the I, and B represents everything in front of the J, okay? Which means now we're going to have what? 4 over negative 5, right? Everything in front of the I is A, everything in front of the J is B. Which means this is in quadrant what? 2. Think about it. We're still thinking X and Y's, right? X's are negative, Y's are what? Positive, quadrant 2. If I do tangent, inverse tangent of negative 4/5, I get negative 38.66 degrees. If you do it on your calculator. But that is not an angle in quadrant 2, is it?
No, it's negative would be in 4.
It's in 4. But I have to find an angle in what? Quadrant 2. So what do I do with this? Take 180 from it, or take it from 180, and I get what? 141.34 degrees.
Get to that one more time. Why don't we do that?
From here, you understand here? So if I figure out negative, if I do tangent, inverse tangent of negative 4/5, I get negative 38.66. That's not a second quadrant angle, so I take it from 180 to get second quadrant. Kind of remember like when we had these reference angles gives us the what? First quadrant angle. But to get that second quadrant angle, we, in essence, add 180. Okay?
You go real quick. We're still up to 38.66.
Do inverse tangent of negative 4/5 on your calculator.
Why do you do the inverse?
Because we need theta. And we got to put a tangent to the negative first by a tangent to wipe it out.
141.34.
Yes, along with this. Y'all just going blank on me when it comes to finding these angles. Now, we've done that several times. Inverse sine. I mean, in the last section with the law of cosines and sines, we did inverse sine all the time to find that angle, right? That's what we're talking about here. Okay, all right. Next example. We want to find the component form of V if we're given that the length of V is 5/2 and theta is 45 degrees. So we go back over here.
Working it backwards, then we should write like the formula they gave us.
Yes,
Okay.
going backward. Because here they say what? They want the norm of V, cosine theta, sine theta. So they gave me the norm of V to be what? Positive 5/2, and I have my cosine theta and my what? Did I say negative? Okay, it shouldn't be. Because length is always going to be what? Positive. I may have said it, but I didn't mean to say it. Length is always going to be positive. Which means here, I can distribute my 5/2. What is the cosine of 45 degrees? And I can distribute my 5/2 here. What's the sine of 45 degrees? Which means this is what? 5 square root of 2 over 4. 5 square root of 2 over what? 4. So yes, we're going backward there. All right, class. Is that enough for today? Huh? I do have another one that I can do. You remember? Huh? No, I do. See? Okay. This will end our talk about vectors, and we will pick up with more things about vectors, kind of like multiplication of vectors next time, dealing with dot product. Okay?